Recording in progress.
Okay. So good afternoon, everyone. So I see there are more people now sitting in front of Zoom than in classroom. So hello, everyone in Zoom. This is a development which I don't like too much. I would like to see many of you here in lecture hall and not the majority sitting at home. The quality for you of teaching and getting the material is certainly better if you come to class. So I strongly recommend that. Otherwise, I will reduce my services to Zoom and will focus more on people here in class. Okay, that's the first thing I would like to point out. Second, a few organizational things. I received emails from some students, obviously lacking a sufficient background in mathematics and statistics for this course. This is a problem. I mean, this is a master course and I cannot start on a bachelor level and introducing in basic matrix algebra and probability. So I cannot repeat a course in statistics 101 and on linear algebra. This is simply impossible. So today I will also make some surveys in between during teaching because I would like to get some information how much you actually know. For those who do not have sufficient background, they have to very urgently to catch up. I mean, everyone needs to know what a matrix is, what an inner product of vectors or matrices is. Everybody needs to know what a conditional expectation is. I mean, and everyone should have seen already, at least in basic form, a linear regression, also in matrix notation. If this is not the case, it will be very, very hard to pass this course. So that means there are two alternatives for those who really don't have this background. Then what you can do is either you do the course in 1 year and you organize the background you need, or you train very hard during the first 2 weeks of this term in parallel in order to get this background. So there is a tutorial offered. So I talked to my colleagues. There is one course which is, so it's a tutorial. I think it's connected to a class, a lecture, which is called Basics of Finance and Decisions Under Uncertainty. So you get to enroll in this course, and there is a tutorial. And in this tutorial, it's also done via Moodle because there are many people signed up for this course, many more than could fit into any classroom. And in this tutorial, there are this basic material is covered in a kind of crash course on matrix algebra, on expectations, so probability, so everything you need to know. That's the alternative. There may be also other tutorials. I don't know. I'm sure there are also tutorials in the web, but it's absolutely necessary that you get on speed because I cannot lower the level in order to introduce everyone and people who don't know what an integral is, that this is something I simply cannot cover here, right? I mean, the objectives for this course, I lined this out on Tuesday. They are quite different. I really want to bring you to speed in learning econometrics and how to apply econometrics. Is extremely important for you and on the job market later. and I have to start on a certain level and have to expect a certain prerequisites. So, I mean, this must be very clear. I think this is mostly true for people in the banking and finance program, maybe not so much from economics. I know there are also people who did my courses in applied econometrics on the bachelor level. I mean, these people are very well prepared. And for those, is partly, some parts is just a repetition. Yeah. But I really have to find a balance between people who already have a very good background and some who have basically no background. That's very difficult. Yeah. So that means you have to work. I do my best, nevertheless, to keep people on board. But you cannot expect that I can serve everything you don't know right from the beginning. This is impossible. You will see today basically where I start from. And this is when you can see as an indication to work very hard during the next week. Okay. So another issue which was discussed is the registration of banking and finance students into the tutorials. That means for all econ students, it's they have to do the tutorial, also pass the tutorial. That means there is a separate examination in the tutorial. For the banking and finance students, it's not compulsory to do the assignment in the tutorial. Nevertheless, I very strongly recommend to participate in the tutorial, because the tutorial, there you train many of these things we do here, in particular related to R. You do exercises. I mean, these are the things you need to know in order to pass the course. I think it's very hard to do the course without attending the tutorial. So that means I suggest the following. That means, so first of all, I also recommend master banking and finance people to do the examinations in the tutorial, because then you earn additional to ECTS. I mean, at the end, this is no harm to you. If you do not want to do these assignments, but you still want to attend in the tutorial, which I strongly recommend, then please make a decision during the next 2 weeks. And if you definitely know that you will not do the assignments in the tutorial, in the Übung, then sign off from this tutorial, and we nevertheless give you the Moodle password so that you have access to Moodle and then all material you need. So that means you effectively can participate in the tutorial, but you cannot do, and you must not do, the examination. Yeah? So that the rule basically should be everyone who is registered in the Übung, the tutorial, so it's the same rule as we have it here in class. Everyone who is registered in 2 weeks is in and also will get a grade. And if he or she still decides then not to make the assignment, of course, we cannot force you, but then you still will get a grade, and then it's basically a failure. Yeah. Okay. So, I mean, we still give you 2 weeks of time to think about this. I think this is fair, also particular for the banking and finance people, that you see where is the level, what is expected from you, and then you can make your decision. But let me repeat again, to be very clear, everyone should attend the tutorial, no matter whether he or she is doing the exam in the tutorial or not. Yeah. I cannot recommend any alternative to that. Good. There was also some questions on these tests. Yeah, there are 2 tests you have to do, which will be either announced shortly before, or they will be not announced at all. And the question was for all people participating via Zoom, whether they can do it then digitally. Yes, of course. I mean, there is then, if we do a test, then I will hand out sheets in class, and in parallel, people have to do in Moodle the same or similar or randomized, whatever questions in Moodle have the same amount of time. And this is then done electronically in a decentral way. So there should be no disadvantage. So if there was also a question, I think in the chat, if someone cannot make it, so I announce a test and someone cannot be here, well, I must say then this is his or her own responsibility. So I will certainly not give then a second chance for those who cannot be here. I very clearly announced this on last Tuesday that I offer you various possibilities to earn credits, to earn points in this course. You have two tests. You have the project. You have during February. You have the final exam. You can afford to skip one of these parts because in total you earn 150%. So, I mean, this is exactly the strategy that for you, if you cannot make it to one of these exams or one of these tests, then you still have all chances still to pass the course, even to pass it with 100% if you perfectly perform in all other examinations. Yeah? So my answer is no, of course, if someone cannot make it, then it's her own responsibility. Good. Then with respect to all Moodle all Zoom participants, I will not monitor the chat. I cannot monitor the chat during class, so it's useless to put some questions into the chat. I will stop from time to time and will give people via Zoom, and of course it's the same as for people here in presence in lecture hall, the possibility to ask questions, but not written questions in the chat, but real questions. So that means a necessary requirement is then that you shut on your microphone, but that's only a necessary but not a sufficient requirement. The sufficient requirement is also to shut on your camera. That means that we see you, and then you can ask the question. My computer is next to the mic here. That means it should be possible, if there are no technical problems, and it should be possible in principle if you speak up and clearly, that everyone here in the room also can hear your question. Okay, so I will stop from time to time during the lecture and then give you the possibility to ask. I think this is easier. I think this is somehow people in the classroom have it a little bit easier because they can raise hands, and this is what I see more or less immediately. And Zoom people then have to wait for these breaks. Okay, so these are the rules of the game. So in this context, yeah, let me directly make the first round of questions for all people in Zoom and also here in class. Yes, please. So please put off your mask and speak up. The structure of the tests, not decided yet. Multiple choice questions, some analytical derivations, some interpretation of output, a combination of everything. But it's a small test, it's only 30 minutes, so I haven't thought very clearly about this. I mean, structure simply means you have a few questions. Yeah. Okay. Yes. So you find all information on where and how and who's the teacher. I also got these questions, who's teaching what and what my name is. And I mean, sorry, I mean, it's your own responsibility to all this information you find in YouFind, where things take place. And with the sign up is that's what I said last time already. If you now decide to sign up in order to participate in the tutorial and to make also the assignments in the tutorial, then please write an email to my secretary. You also find her name on the website. If you go to my website, you find her, Julia Brandstetter. Tell her, okay, you would like to get registered, okay? If you make the decision that you do not want to do these exams, this examination in the tutorial, but you still want to attend the tutorial, then ask her, write her, and ask for the Moodle password. Okay.
I also.
Yes, there's a question here. Yeah, speak up.
Could you please repeat the name of the tutorial for the basic mathematic stuff?
Yes, I should. This is called Basics of Finance and Decisions under Uncertainty.
Okay, thank you.
I also have a question.
Yes.
Is there any way that this course could be moved with like 15 minutes or 30 minutes or something like that? Because a lot of students didn't make it today because we had basics of finance before. Or if the course on Tuesday can be like in class and on Thursday it can be online, I would suggest.
Okay, the question was this whether the time of the class can be shifted to some lecture before. I mean, no, it simply cannot. I mean, this is from an organizational viewpoint, that's too complicated. No, I mean, you should have sufficient time between these lectures to change rooms. I don't see the reason. No, I mean, the class is simply too big with more than 200 people registered for this course. No, in order to shift around times, this is not possible.
Okay, thank you.
More questions from the audience?
Yes, may I ask a question?
Yes.
Okay, we had a voting on last Tuesday to sit in the class or to take the course online. However, before today's lesson, I could not find an updated voting, and then I could not vote. And what I saw, the old votings were displayed still. So can we repeat this voting on daily basis for each course, or as does the vote that we put last time bind us for the whole term of the course?
I don't repeat, well, I don't understand the question.
Okay. And last Tuesday, I voted to take the course online, okay? And as there are limited seats in the classroom, and we cannot come all together, and today I wanted to vote to take the course in the classroom. However, I could not find an updated option link to vote for the today course.
Okay, I understand. Okay, good. Yes, good question. So on Tuesday, my secretary put in this tool where you can reserve your seat before. Yes. Now I didn't do it because I thought that in principle we have sufficient number of seats anyway. But I still can do it, of course. It's no problem. I can do it. But in principle, basically everyone should get a seat, right? I mean, we have close to 200 or a little bit more than 200 registrations. Yeah, I do know that some people will never show up. So I discount this a little bit, and I think we have something like 189 seats which are officially available even under Corona restrictions. So therefore, I thought it's not really necessary that you reserve upfront, but you can come. I think the risk that the room is really crowded, overcrowded, is very, very low. That's the reason why I didn't do this reservation scheme in today, but I can, of course, we can do it now for every class. Yeah, but I definitely would appreciate to see more of you in class, it's definitely easier than via Zoom. Good. Okay. So this next round of questions then will come, but now we have to start with the material. Good. Okay. So this is what we discussed already. I introduced things a little bit more formally. Now, at this point, let me just take the opportunity. Now I assume that this is a representative selection of students in this course, because doing this now via Zoom is a little bit too complicated. So who has never seen a matrix before? So please hands up and please be honest. I need this information. Who does not know what a matrix is? Okay, there's one. Okay, so you have to do some homework. I'm sorry. Yeah, okay. All others know what a matrix is. Good. Okay, so who has never seen a linear regression before? You saw a linear regression, but without matrices. Okay, good. Okay, so you all know what a linear regression model is. Okay, very good. Good. This makes my life a little bit easier. Good. So, okay. Who does not know what a conditional expectation is? Okay, there are a few. Who does not know what an expectation is? Are these the same people? No. So that means you know what an expectation is, but you don't know what a conditional expectation is. Okay, so you don't know what conditioning is. That's hard to believe. Maybe you have to look at a little bit in your notes. I mean, conditioning, to understand the role of conditioning is extremely important, because econometrics at this level in particular is about conditional expectations. So conditional moments, that's the first conditional moment. And it makes a huge difference whether you condition on something or you don't condition on something. Okay? So, and I mean, this is something you have to catch up immediately. Yeah? Otherwise, it will be very, very hard. Yeah? Okay, just to make it very easy, conditional expectation, think about an average, right? I mean, this is an average, that's a population mean. Of course, we estimate it by a sample average of a random variable y. Okay, and we condition on something, on some other variable. So for instance, I do a survey here in class. I ask you about, I ask you this question about your knowledge in math. Okay, and now I make a condition. I do not ask everyone. I say, okay, now I would like to know this from all male person or all female person. That would be the same as putting in here a dummy variable, which is either one for male or for female. And then I take an average of your responses for male and female. This is what conditioning is. So it is a function. If there would be no conditioning, then it would be the unconditional expectation of y, and the unconditional expectation of y is deterministic. Why is it deterministic? Often that is not very well understood by students. Y itself is a random variable, but the expectation of a random variable is not a random variable if we take the unconditional expectation. This is then deterministic because it's an integral over a density. So it gives you a number at the end, and this is fixed, this is deterministic. But if we condition on something, that means we compute a conditional expectation, then it is a function depending on this random variable here. It changes depending on what the value of this x is, right? This is the random variable, and these little x in these little x here, this is the realization. So in my dummy example, that would be, okay, 1, say, for female and 0 for male. So either 1 or 0. Okay, but this is a random variable. So that means whenever I put in here the conditioning, then the whole function, the conditional expectation, it becomes random because it's a function of a random variable. That's very important to understand. To give you already maybe the most important example in our context, I mean, one example, which will come later anyway, is that I say, okay, the conditional expectation of yi given xi. So by the way, whenever I use this notation, then this means this notation with the xi here simply means that xi takes some certain values. So I can take any value. So basically, I mean, I could write it in that way, but this is the shortcut notation. Okay? So, well, this is something which is generally unobservable, so it has to be estimated from the data. You have data on y and you have data on x. And we would like to know what the conditional expectation function of y given x is. Okay, how can we do this? Well, we impose some structure, we make some assumption, for instance, in the sense that I assume that this is xi prime beta. Yeah? So, and beta is a parameter which I either know or I need to estimate. So that means that is a linear form. This is the most simple form you can think of. And now you see, okay, this conditional expectation is obviously a linear function of x, of this random variable x with some parameter beta. Yeah? So this is what we call a parametric model for these conditional expectation. This is what we are talking about. Okay. So the conditional expectation function plays a key role in econometrics. Therefore, I spend a few minutes now on discussing some properties thereof, because you will use this, you will need this again and again during the course. The first one is the so-called conditional expectation function decomposition property, which essentially says that any random variable y can be split up into its conditional expectation given something, so some other random variable, no matter on which you decide to condition on, yeah, plus a remainder term. This remainder term is this epsilon. Yeah, that's what we call the error term typically. Yeah. So you will see immediately now, if you take expectations, so if we take the expectation now of y, then this means I take the expectation of the unconditional expectation of y given x. And here I need to use the law of iterated expectations you have learned in some statistics course, and you should know, okay, according to the law of iterated expectations, the unconditional expectation of a conditional expectation is what? It is the unconditional expectation. Okay? And then the rest of this equation was this epsilon. So I need also to take the expectation of the epsilon, and this has an expectation of 0. So that means what comes out is by construction the same term on the left side and the right hand side. Yeah. Okay. I also could take the conditional expectation of this. Yeah, so I take the conditional expectation now of this. So the conditional expectation of y given x is, of course, itself the conditional expectation. So I do not have to change anything here. Yeah, the conditional expectation of a conditional expectation is the conditional expectation. Yeah. Plus the conditional expectation of the epsilon given xi, and of course this must be equal to 0. And then of course I also get the same on the left hand side and on the right hand side. So this means this decomposition can be done without loss of generality. Any random variable can be split up into these parts. Why is this important? Well, think about a linear regression or general regression setup. We would like to explain the output variable y with some input variable x. Okay? So this means that this random variable y can be decomposed into one part, which is a 1-by-1 function of x. That means this part here is perfectly correlated with x by construction. It is a function of x. Yeah. So for instance, if we just take this example from before, that would be the example where the conditional expectation is xi prime beta, then you see xi prime beta is a function of x. Beta is deterministic. Yeah. So that means this part here is something which is perfectly correlated with x. It's the function of x, whereas the other part, the remainder part, the epsilon, is exactly the opposite. It is by construction something which is orthogonal to the other part. In other words, it's completely, not completely, it is just uncorrelated with x. Yeah? So that means when I want to explain y by x, then I can mathematically decompose the y into some part which is perfectly explained by the x, this is this part, and a remainder term which is completely disconnected from x. This is very important for regression, this decomposition. And this is something we use very often. Okay, good. So the other important property of the conditional expectation function is that, now let me ask the following question. Let's assume m of x. M is some function. It can be a linear function, quadratic, exponential, whatever, any function, some function. And my question is now, or my aim is, I would like to predict y. And the question is which function of x is the optimal function such that I can explain or I can predict the y as best as possible. And if I say as best as possible, of course, I need a mathematical criterion. This is what you see here. I'm looking on the error, the prediction error, so the difference between yi and my prediction, right? This is my prediction. Xi is the input. M of xi is the prediction for y. And this is the realization. This is what I actually observe. That's what I observe, and this is what I predict. The difference is the prediction error. And I square the whole thing. So it's a squared prediction error. Okay, and then I take the expectation thereof. This is the mean squared error. So I'm asking for, okay, which function minimizes this mean squared error? And the answer is this m function must be the conditional expectation. So if I choose this as the conditional expectation, in other words, the optimal choice would be that m is the conditional expectation of yi given xi. This is my optimal prediction for y. Well, is this helpful in practice? It's a nice mathematical result, very simple results. I don't prove it here. You find the proof in any textbook. Yeah? You can look in the Engres-Pischke book if you want. I mean, these are 2 lines. It's very simple. But is this result helpful? No, in the moment it's not helpful because, I mean, it's nice to know that this function here is the optimal function. But now I would like to know how the function looks like, right? I give you data y, I give you data x, but I don't tell you how the conditional expectation looks like. Well, in order to make this operational, I have to impose some structure. So either I try to estimate this structure here non-parametrically from the data directly, or I impose a parametric structure. And the parametric structure could be, for instance, this linear model, this linear form. Okay, good. And then the last result is the so-called ANOVA theorem, analysis of variance. This is where it stands for. We need this also from time to time, therefore I present it here. This is now, the focus is the unconditional variance of y, and we can easily show, I also skipped the proof here, that the unconditional variance of a random variable can be, again, split up into 2 parts. Namely, it can be split up into the unconditional variance of a conditional expectation. So for those of you who still have problems with conditional versus unconditional and mean and variance, I mean, if you understand these things here, I mean, then you're in business. Yeah. So how can we compute in a variance of a conditional expectation? Well, the first thing to know, and this is what I said already, of course, we must realize that this thing here is random because it's a random function of x. Yeah. If it would not be random, then of course it would not make much sense to compute a variance thereof. Or in other words, if that would be not random, then the variance of something which is non-random is 0. Then the whole thing would be 0. Yeah. Okay. So in principle, you can think of that. Okay, I compute an average of realizations and I condition on various realizations of x. Yeah, in my simple example where x is a dummy variable, it would be easy. I just condition on male and I condition on female. Okay, and for both constellations, I compute the average and then I compute the variance of these two averages. So it would be a variance only of 2 realizations. But okay, that's very easy, but it exists. Yeah, okay. And the other part here is the unconditional expectation of the conditional variance. Now, what is the conditional variance? Now, this is the variance of yi. This is basically the variability of your responses, given that you are male and given you're female. So I again take both parts of you, and then the conditional variance of yi measures the variability of y within each group. So then I have 2 variances. And then I take the mean thereof. Okay, and then we can show if we then add both things together, then we get the unconditional variance. Okay, in very simple words, you can think of, let's just take the example of the 2 groups of male and female. Yeah, then this here is the average variation within a group for male and female. And this is the variability among groups, between groups. Okay, and therefore this is also called analysis of variance theory, because you decompose into variation within groups and variation between groups. And this is something we do very often and we need very often. When we come to panel data, we will be confronted with similar results. Good. So now I introduce the conditional expectation function. Now, what is the connection now to linear regression? So now I introduce linear regression I introduce it in a way you probably did not see it so far. I introduce it as a population regression problem. So whenever I talk about population moments, what I mean by that, this is the theoretical moment, the theoretical mean, the theoretical variance, the theoretical covariance. These are all population moments. Yeah, and we can formulate a regression problem in terms of population moments. So I will show you. So let's assume we have the following problem. I would like, so here I have x. X is again a vector of regressors. Beta tilde is a vector of coefficients. You can interpret this, I mean, this is just a weighted sum or a linear combination of x's. And this linear combination is determined by these weights, beta tilde. And I would like to know, okay, how should I choose the weights, beta tilde, of this linear combination, such that this function here, this linear function, is a best possible approximation to yi. I mean, this is the regression problem, right? I observe yi, and I would like to describe yi by a linear combination of regressors. Okay? So, and in terms, and it is a population regression problem because there is an expectation here in front. So I asked the question, okay, which beta tilde gives me the that combination which minimizes the mean squared error. That means the average squared deviation between this guy and this guy. Yeah? Okay, Good. And then in principle, it works in exactly the same way as for sample moments. Well, I have here an optimization problem. I need to compute a first order condition. That means you take this function here and you compute the derivative of this function with respect to beta tilde. I think I don't need to do this. For those who still do not see immediately how this works, and use this as a small homework. I mean, the derivative of a quadratic function, I mean, gives a linear function. I mean, you get the derivative. I mean, you get a 2 times the whole expression. And then, of course, the expression itself, the derivative of this expression with respect to beta tilde. Of course, then you get an xi in front. Here's the expression. Of course, I also could squeeze in the 2, but the 2 cancels out anyway because I set the first order condition equal to 0. And then it doesn't matter whether I multiply it by 2 or not. Okay, so this is the first order condition. Okay, so and from this first order condition, of course, this is what I can solve directly. Let me just finish this point here. So this is maybe what I can briefly illustrate. So I can just write this first order condition as the expectation of xi, yi minus the expectation of xi transpose beta tilde, and that should be equal to 0. And of course, I also can put the beta tilde outside of the expectation because it's a deterministic anyway. And then I can put it on, I solve it for beta tilde, and then I get the expectation of xi transpose inverse times the expectation of xi transpose yi. Okay, so there was a question. Okay, this is sorry? Yes, of course. The prime is a transpose. Yes. Yeah. The prime is a transpose. Okay, good. Well, it should be clear. So now, let me ask, do you understand how this thing looks like? This is a matrix. What you see here, this is an outer product of two vectors. Is this clear to everyone? Xi is a vector, a column vector of the dimension k by 1. Okay? X transpose then is the same vector transposed. So if I multiply these two things together, this is what I call an outer product. What comes out? A matrix. Right? A matrix of the same dimension. It's in this case k by k. This is a k by k matrix. Okay? And how does this matrix look like? Well, it's the expectation of, well, what is the first element? It's xi1 squared. So it is the realization of regressor number 1 at observation number I, but it is squared. The next is then xi1 times xi2. Here's the same, xi1, xi2, it's symmetric. And then, of course, we go on. And here the next squared element is xi2 squared, and so on. Okay? And this is the k by k matrix. Okay? And this matrix here, what is this matrix? The dimension of this matrix, this is a k by 1 matrix. Is this also clear? Okay, this is k by 1, this is k by k, and what comes out, the vector, the overall vector is k by 1, as it should be. Okay, for those who still struggle with that, then you have a clear homework. I mean, you should not lose time with these matrix multiplication issues. Yeah? You should clearly understand what it means. And well, what that means intuitively, I mean, this is nothing else than a second moment matrix, right? I mean, you see it clearly, the diagonal elements, these are all squares. So we take the expectation of a squared random variable. This is a second moment. Okay, and the other terms, these are all cross moments. The expectation of one variable times some other variable. And what is this intuitively? What does this describe intuitively? Well, it's closely connected to a covariance. If the mean of these random variables would be 0, then this would be exactly the covariance. This would be then the covariance matrix. Yeah? If the mean is not exactly equal to 0, okay, then we have to subtract the mean. But I mean, you always should have this intuition. And the intuition is whenever you see an expectation over such a cross product, you should know, aha, this is the second moment matrix. I mean, this determines the covariance between the two variables. Yeah, and if it is just a square, then of course it's a covariance with itself, which is a variance. So it's a second moment matrix. Yeah, for me, it's very important that you also understand how to read these formulas and that you don't accept them just as some mathematical expressions. Yeah, you have to understand what is behind, and that's not rocket science. Okay, so let me stop for 1 minute, give the Zoom people the possibility to ask urgent questions.
I have one algebraic question actually. Where does the transpose come from in the second line? Like, I don't entirely get how we get from the first line to the second line.
How do we come from the first line to the second line? You mean this slide here?
Yes. On your notes.
In which transpose do you don't understand?
Of the first expectation, the -1, like where does it come from?
The first expectation, there is no trans.
Not transpose, sorry. I just algebraic, like from an algebraic point of view, I don't understand like how, apart from getting the beta out of the expectation, how we get to the value of the
Power of -1.
Well, I don't understand what the problem is now. It's a little bit hard to do it via Zoom. Try to solve it yourself or ask me later, please. Yeah. Otherwise, I lose too much time. Sorry. Further urgent questions? Okay, good. So we have constructed, I mean, this is what we call you could argue this is the population, well, I should not call it an estimator, well, but it's, yeah, I mean, it's the population version of the ordinary least squares estimator. Yeah. And now how is it connected to the ordinary least squares estimator? You know, well, very easily. Maybe let me also present this right away here. So let me just write down the expression again. So we have the, just this expression here, we have the beta equals to the second moment matrix, xi transpose inverse times expected value of xi prime yi. So is this something I can observe? No, I cannot observe it because I don't know what these expectations are. So I need to estimate these expectations from the data. So how do you estimate an expectation, an unconditional expectation? Well, you estimate it by the sample average. Yeah? I mean, this is one possibility, but it is the most straightforward possibility to estimate a mean. So that means what we do is, well, we estimate no beta hat. I put a hat in here. So I also need to put a hat in here and I put a hat on top of this expectation. So that means now I estimate these expectations. And how are these expectations estimated? Well, I just take a sample average over all realizations of xi prime I see in my data. So it's a sample average. Okay? And this thing here, and I'll also leave this to you as a mini homework for those who still have to repeat a little bit on matrix algebra. That's your job now to verify, but please do it if it is not clear, that this expression is the same as this expression. Namely, this is the same as the inner product of the corresponding regressor matrix. So you can either write this as an inner product of the corresponding matrices or as the average of the outer product of the corresponding regressor vectors. That's the same thing. Okay. So, okay, I have to make, so that means this is what I estimated here. This was this part. So maybe I should write it here separately, otherwise you get confused. So this is xi transpose, what I computed in here. So, and I need, in the same way, I need an estimator for xi yi. I think now I know what your question was, because there is the transpose. Yes, maybe this was your question. Because there was a mistake. Let me correct this. I just realized that this transpose here is wrong. Please correct this. Maybe this was your question, which I did not understand, which means that you also have to erase this transpose here. Sorry for that. I mean, there was simply a typo. There's no transpose. Yeah, otherwise it doesn't make sense. Yeah, okay. So, okay, so I need to estimate this also by a sample average. It's 1 over n sum over these realizations xi, yi. And please, also this has to be verified by you. This is the same as the inner product between the regressor matrix and the vector of left-hand variables. Okay, so, and if I plug this in, then my estimate is x prime x, and of course I have to take the inverse thereof because the second moment matrix is inverted, times x prime y. So here's the good old ordinary least squares estimator, and you see directly the connection to its population version. So the ordinary least squares estimator is nothing else than a sample. It's just an estimate, a sample estimate of its population version. That's the question, yes? I corrected, I erased this transpose because it's just xi times yi. Yeah. And I corrected also, here was a transpose which I erased, and here was a transpose which I erased. Yeah. Okay, good. So by construction, this was the first order condition again. But what does this first order condition mean? Look on this expression, this yi minus xi prime beta, we could give it a name, we could call it epsilon. Well, later on it will be the residual, because the estimated version thereof is the residual. And what do we see? Again, we see an expectation of a product between x and epsilon I. Okay, what did I tell you just 5 minutes before? Whenever you see an expectation of a product of two random variables, then it indicates a covariance or something which is related to the covariance. In this case, it's the covariance. It's the covariance between xi and epsilon I, because the expectation of epsilon I is equal to 0. And this makes the whole expression a covariance, a real covariance. So it tells us, okay, that the regressors and the errors have a covariance of 0. And if the covariance is 0, that means the correlation is 0 as well. So they are uncorrelated. Yeah. So that's a key property. That means we find our regressor combination, the optimal combination of the regressors in such a way, such that the error term, that means the leftovers, which we cannot explain, which is basically outside of our model. This is something we cannot explain with our axis. This must be, however, uncorrelated with the axis. It makes a lot of sense, because if it would be correlated with the axis, then of course we should take it into account in our model, and we would get an even better prediction of y. Yeah? So if this is the best possible combination of the axis, then everything what cannot be explained cannot be correlated with the axis anymore. So it's outside. Yeah? Makes sense. Good. Next aspect, which we also will use from time to time, is here it is called, I use this language from Pischke and Engrist, anatomy of multivariate regression. So the question is as follows. So let's let's suppose we have a vector beta. This is what we just have computed, and that's a k/1 vector, right? I mean, this is now, these are numbers, and these numbers give us now the optimal linear combination of x's in order to explain y. Good. This can be computed or can be estimated using this formula here. Or respectively, if we bring it to the data, then this formula here. Good. Now I ask the question, but what I just have constructed is an analytical expression for the entire vector. Yeah? So this gives me the entire vector. So the question is, how can I compute numerically just one single element here? For instance, I would like to compute just this element here, the second element. Yeah? No matter which one element out of this vector. So how can I numerically compute this? There's a nice result, which we also use from time to time in econometrics. In panel data, we will use it also again. And this is the result which is shown on this slide. So this is beta k. So k would be 2 here, so the second parameter. Yeah? So that's the coefficient associated with the kth regressor. So how can I find this? I can find it as the slope coefficient. The slope coefficient for the kth regressor is given by the covariance between yi and regressor number I. However, this regressor has a tilde on top, which means it's not the regressor itself, but it is the residual from a regression of x on all other covariates. Covariates is just another name for regressors. I use this from time to time. Okay? So what I need to do is, in order to compute such a single value, is I have to run a regression of my regress of interest, number I. I put this on the left-hand side of such a regression and regress it on all other explanatory variables in the model. Okay? And from this regression, I take the residuals. And what do these residuals tell me? These residuals capture everything which is, it is basically the remainder term, everything which the variation which cannot be explained by the other covariates in X. Right? Whenever I compute a residual is always a remainder term. It is always that part in a regression which I cannot explain with my regressors. Yeah? So when I now regress the regressor number k on all other covariates, and I take the residual of this regression, this is actually this thing here, yeah, then this is just the leftover. That means that part in the regressors which cannot explain regressor number I. Okay? So the same is here. So, and then it can be shown analytically, I don't provide a proof here, that if we compute the beta k as the covariance of this term divided by the variance of this residual term, this is exactly this coefficient in here. So that means we can separate out all individual elements of such a vector. So we can estimate them or compute them separately. So I have one way to compute them all together in one block. This is what I did here with this formula. This gives me all together. But if I want to have a closed form solution, a closed form expression, and sometimes I need this for one or a single value in here, yeah, then it is exactly that one. Okay? In the moment, this looks a bit abstract, but you will see during the course that we actually need this result several times. Yeah, so keep it in mind. Good. So, justification for regression. Why should we use regression? Regression, of course, means that I try to capture a linear relationship. So I have some variable x, I have some variable y, I have some data, which maybe looks like this. Okay, linear regression simply means, okay, I fit a regression line here. And it's linear. Okay, is this a good description of the data? Well, it depends on the data. And sometimes a linear approximation is good, sometimes a linear approximation is bad. Yeah, a linear model is the most simple econometric model you can think of. And sometimes people criticize this. So the question is, what is the justification for doing such a regression? Okay, I can give you 3 arguments. So I don't tell you that you always have to do regression, but I mean, there are 3 arguments which are quite valid in many situations. The first is, and there's a little theorem, which I also will not prove here, basically says, let's assume that the conditional expectation function is linear. Okay? So in other words, the conditional expectation of yi given xi is a function which looks like this. However, I don't know what the beta is. Yeah? So that's what I assume. Then the argument for linear regression is that the linear regression gives me an estimate of the conditional expectation function. In other words, the population regression function is it. It is the conditional expectation. So if the conditional expectation function is linear, then it's identical to the population regression function. It's the same thing. Okay? When is it linear? Well, often it's not linear, and often this might be a hard assumption. But in some situation, actually it is. So if the vector y and x is multivariate normally distributed, so if this is normally distributed and this is normally distributed, so this is a joint multivariate normal, so a joint normal distribution. Yeah? Then we can show that the conditional expectation of yi given xi is linear in x. It's an automatic result. So if you believe in normality, then this comes out automatically. And this gives us then, of course, a very strong motivation for estimating this guy here, so basically the beta here, by linear regression. Yeah? The other situation we also will talk a bit about in this course is if a regression model is saturated. So you don't know yet what this is. Maybe some know from my bachelor courses. A model is saturated if there is a separate parameter. There's a typo. There's an E missing. A separate parameter for every possible combination of values the regressor can take. So let's assume I have a regressor which can take, say, 20 different values. Yeah? Let's assume it's a discrete variable which can take on 20 values. And now I put in 20 parameters in my model to capture each possible realization of this regressor. That's a fully parameterized model. This is what we call a saturated model. In this case, it can be also shown, because the question is whether such a model is really useful, but as a benchmark. And in this case, we also get linearity. So apart from this, there are two other justifications for using linear regression. And this is given by this theorem. This is the best linear predictor. So if I ask the question, which linear function? So I take all possible functions which have this form. Of course, what is unknown is the beta. Okay, so I have a set of infinitely many linear functions, and I ask the question, okay, what is the best combination, the best linear prediction of y given x, and best means in a mean squared error sense. And then, it's basically, it's given here that this function here, xi prime beta, which I can estimate by linear regression, is the best linear predictor. So regression gives me the best linear predictor among all possible linear forms. It gives me the best linear combination of regressors. And the other, I mean, this maybe I should put this here separately. So I should separate these from the theorem. Oh, this is a mistake. This should not be in the theorem. This is just to recall. This is what we have shown already. So maybe instead of the hence here, you can put in here recall. The conditional expectation is the best minimum mean squared error predictor of y given x in the class of all functions of x. Okay, so this is the best what we can do if we search among all functions of x, and this is the best what we can do if we search in the class of function of all linear functions. So therefore this is the best predictor in a mean squared error sense. And this here is the best linear predictor. Okay. And the final justification, and I think, to my opinion, this is the most important one, is this one here, this theorem. Namely, it says that the function xi prime beta provides the minimal mean squared error linear approximation to this unknown conditional expectation. So we take again the perspective, I have data y, I have data x. I would like to estimate this, but I don't know what the form is. So I don't assume that it is linear. It can be anything. It is simply unknown. But then I take a linear regression in order to find that combination of the regressors, beta tilde, which gives me the best possible approximation to this unknown conditional expectation. So that means a regression can be always understood as a best possible linear approximation to an unknown nonlinear, possibly nonlinear relationship. And sometimes it's useful to know this linear relationship. Often it's useful. Of course, there are also situations where it's not so useful, where we really need a nonlinear model. Okay, good. That's it. How to estimate beta. This is what we just have done. So I provided this already before, but here's basically the slide. I see here's also this typo. It's somehow a persistent typo. Also here, please. There should be no transpose in here. This is wrong. Good. Okay. So now let's have a look on some data. So I just have to stop screen sharing, but then I will open it again. Just a second. To put these separately to make this work. Okay, so now I should be able, yeah, to switch back and forth. Okay, so now we look on some data. This is data which I got from this package. You see the package. This is this AER package, which contains a lot of nice data sets, which we also will use here in this course. So we have to load these, I load all these libraries. So they contain different things we need from time to time. So I just load them all in. I mean, it's no harm to load in a library which you don't need necessarily. This is the data. It's called Duncan data. I don't know exactly where it comes from. It's just an illustration, so I hope you can see it. So this contains data. It's a data frame. It's 45 rows, 4 columns. It's data on the prestige and other characteristics of 45 US occupations in 1950. You see here on the left-hand side, they are all different occupations: a chemist, author, professor, dentist. Okay, and there are some categories of income. Okay, so the dentist here is doing much better than the professor. Education for the professor is higher than for the dentist. Okay, and here is the prestige according to, I don't know how this is, maybe on some survey, I don't know. Yeah. Okay, so and now what we can run, I mean, here's just so here's just the table you get directly from the data. I mean, this is what you can reproduce from the data. I can show it here directly. So I close this again. So a summary, the data, then it opens here. I mean, these are simple commands, I guess you learned already. It gives you a simple summary, some summary statistics of these few variables in the data set. Okay, and I would just like to use this as a first illustration of a linear regression. Yeah, as you learned in class, in the tutorials. I hope you got already a little bit of an introduction. I have to find it again. So here we go. Okay, so here, this is the regression. I mean, in R, it's very, as you probably learned already, you can just click on a line and you can run each line individually. I mean, you can even mark individual variables and then you can show them also individually if you mark them. And you click on, well, I have a Mac here, but I guess it's the same for other computers. It's typically the Enter and Command key. And then you can look on each individual variables. So here I run this linear model. LM stands for the linear model. It's what we learned already. This is the left-hand variable. It's followed by 2 regressors, education and income. We would like to know, okay, how strongly is education and income related to prestige? Or in other words, how determine these variables a prestige? Yeah, if we write it in this way, then an intercept is automatically included. We also can exclude it if we don't want an intercept. This is rarely the case, but sometimes we don't want an intercept. I mean, then we have to type it in and then it's estimated without an intercept. So, okay, good. Nothing happens. Well, here the model is estimated, but the regression output is not shown yet. So that means we also have to type in summary of this regression. This is the name of the regression, what I have chosen, model 1. You can choose whatever name. Okay, then we get the summary, and this is the regression in here. Okay, so this is the first example now of the ordinary least squares estimator. So what you see here now, this is beta hat. So this is the linear combination of an intercept. Intercept is just a column of ones. Yeah. And education and income. This is the linear combination which optimally describes the left-hand variable prestige. And of course, both, as expected, both are somehow positively related to prestige. The more income and the more education, the more prestige is the job. Okay, so let me also show this, to do this by hand. I think this is, of course, you typically don't do this, but I think for you, for those who just learn R, and also still have a little bit of problems with matrix algebra, I mean, I think this is very, very good just to do this by hand. So by hand means, okay, I define now the vector of left-hand variables. Yeah, and this is can I do with this command. You see the data set is called Duncan. This is just the name of the data set. And with this dollar sign here, and then I add prestige, this simply means, okay, I take the variable which called prestige out of the data set Duncan. Yeah, and as matrix means that I just use all these values and I put them into a matrix, or in this case, it's a vector. Yeah. So this is Y, and then this Y shows up here. So see whether I can move this a little bit. So you see here now the variables show up. Here's the Y. You can do this also directly by command, but you also can click in here. Yeah. And then you see here, this is Y. This is my vector of left-hand variables. Okay. So then I can do the same here for the matrix. You see the matrix here, ICBind is a command which stands for column bind. So I just bind together one column next to the other. Yeah, what is the first column? Here I just generate, this is a vector of ones. Yeah, so you can work out this command yourself. This creates a vector of ones, which has the length, basically the number of observations contained in Y. Yeah? So n, in our notation, this is n. It creates a column vector contained of ones of the length n. Okay, and this is what I bind together with the variable education and the variable income. So I have three variables next to each other. Okay, I create this. And I also can, sorry, I should do this here. Now you cannot see it. View, with view X, you also can type it directly. Yeah? And now you see this is my matrix. Yeah? For those who still have problems also with products, how products from vectors and matrices work. I mean, here in R, you can directly see them and you can do these operations yourself and you see what you get out. Yeah? So that means this is a matrix of 3 columns. This is my regressor matrix X. So, and here I do now the regression by hand. Now I compute beta hat by hand. Okay, so you see here, this is an R command, which is called cross product. Well, it's just a name. It's maybe not the optimal name, but what is meant by R is an inner product. So what is computed here by this command is X prime X. Okay. Inner product of the regressor matrix X. The solve in front is the inverse. This is command which means solved. It's basically a solver of linear equations. That's where it comes from. But it's the inverse. This stands for the inverse. So this computes the inverse of X prime X. Okay? So, and this is multiplied. This sign here is just a normal matrix multiplication. Yeah. And this is now multiplied by the inner product between X and Y. So this is X prime Y. So X prime X inverse times X prime Y. This is my formula. And I give the formula a name and I call it beta hat. The name I can choose. And here, of course, you can always work with this arrow, but if you don't like the arrow, you also can use equality. I mean, it's a matter of taste. Yeah? But I mean, with this arrow, this basically means that, okay, I compute this expression and then I assign this expression to this name here. You have to get used to that. Okay, I compute it. And here you see, now you can compare these numbers. These are the point estimates. Now you can do it yourself. And these are exactly the same numbers as we saw it before in the regression output. Yeah. So in the next line, now I can compute the residuals. I call them E hat. These are the residuals. How do I get the residuals? Well, if I just take Y minus X times beta hat. Yeah, so that means what I have computed here, the residual. Where do I have it? Oh, okay, it's not in here. I write it down. So the residual is y minus x times beta hat. Yeah, and this can be also said as the difference between y and the fitted y. This here is the fitted y. Yeah, this is my prediction of y, and the difference between what I observe and I predict, this is the residual. Okay, and this is what I have computed here with the residuals. So now let me briefly illustrate these results before that. Now I would like to compute one of these elements here separately. Let's take the second one. This is the income variable. Yeah, I would like to compute this separately. Now I can use this result from before, basically the result which we have discussed here, this result. So now let's just do this. Okay. So, okay, what do I have to do? I'm interested in the coefficient of education separately. Yeah? So remember this value, it's 0.45 something. Yeah? So now we try to quantify this individually. What do I need to do? Okay, I run a regression of education on all other variables in the model. Okay, this is only the income variable, and the intercept, of course, is automatically included. Okay, so I run this. Then, okay, I can show it again, but I mean, this is not so interesting now, this regression. So in the next step, now I would like to compute the residual. Okay, I can do it again by hand, as I just did, but I'm a little bit lazy. I do not want to reinvent the wheel. Of course, there are automatic commands also in R, and this is the command. Yeah, so basically you put in the whole regression equation. Again, this is what I just run. You put it in brackets and you put residuals in front. And then R is doing in one step, doing the regression and directly computing the residuals out of this regression. And then I give it a name. So I call it RES, stands for residuals from this model 2. But that's arbitrary, which name you pick in here. Yeah, okay. Good. So, and now comes the last step. Now I'm putting these residuals again into okay, now I have to add these residuals to my data. This is what I do. I just take the Duncan data, and with this cbind, I just add an additional column to the data. Okay, I will show you. Okay, let's click on the Duncan data. You see, now I just added this fourth column, this one here. This has been, this was the original data, and now these are the residuals, because I treat them now as an additional variable for my purposes. Okay, so and now comes the last step. Now I run a regression on my prestige, that's the left-hand variable, and I run it because I would like only to evaluate the coefficient of income. So I run my prestige variable on the residuals of this new created residual variable. Okay. And the summary of this is you get this coefficient in here. Okay. So we have computed this coefficient here separately. Okay, this is just the result I've shown before. Good. Yeah, this is basically what I wanted to show you here. Let's switch back to my slides. Yeah, this is basically the table. These are just the results. I mean, you can replicate this yourself. Yeah. This illustration is also in R. I do not want to go through all. I mean, this is just an illustration now of this education variable. These estimated coefficients. The red one is just what we estimated, or it's the green one. I don't know. One of these. And the other coefficient, the other regression line is the regression line we would get if we would leave out income. Yeah. So one regression line is where we only regress prestige on, sorry, it was prestige on, what was it? Education. Yeah. And the other regression line was prestige regressed on education and income. So the difference between both is you leave out in one, you leave out the income variable. You see that you get a slightly different slope. That means you get a slight bias in one estimates, which means it is important not only to regress prestige on education, but you also have to control for income. Now we will come back to this later. Good. There's some other illustration based on wage data. I think this is what I can leave to you. It's basically a regression of wages on years of education. That's a very important topic in labor market economics. So we would like to know, okay, how much does education pay off in terms of wages later on? This is a heavily researched field. I mean, this is just a Mickey Mouse illustration of such a relationship here. Also, this relationship will be explored in much more detail during the course because there are some econometric pitfalls we have to take into account. Here, I just use this as an example as one linear regression. Okay, good. I think for time reasons, I skip this part here on the conditional means. Yeah, I mean, this is not super important at this point. It's just some additional information. Good. So I skip this. Good. So the next section now is, this basically was all around conditional expectations, yeah, and how to do and what conditional expectations mean and how they are linked to a regression function. Now the next bigger section now is on formally introducing ordinary least squares and the major properties. And for me, this is actually a very difficult section, not difficult in terms of the material, but difficult in finding the appropriate level and the appropriate speed. Yeah, because I mean, for some of you, this is material you know already. And for some of you, this is very new. And then, of course, it's a lot. And I have to find a good balance. And I only can find a good balance if you also let me know from time to time whether you can follow or not. Yeah. So let me just use the last two minutes still to say a few words on, or at least to start with the assumptions. Every econometric model or any estimator we derive in econometrics starts with assumptions. Assumptions are boring for students, and you tend to overlook the assumptions, but the assumptions are so super important when you want to understand under which conditions your estimator is working well and under which conditions you have a problem. So it is important to look on these assumptions. Yeah. Okay, what are the key assumptions for linear regression? Now I do this a bit faster, but you also can let me know if it is too fast. The assumption number one is that we need a linear model, and with linear model, we mean a model which is linear in the parameters, not linear in terms of the variables. So for instance, if I regress, for instance, the log of yi, and I regress it on the log of xi prime beta plus epsilon I, so that means I use logarithmic variables instead of plain variables, then this is still a linear model because the coefficients themselves, the betas, they enter linearly. Yeah. So when I talk about a linear model, then I don't mean a linear relationship necessarily between y and x, but a linear relationship between beta. Yeah. So, the betas enter the model linearly. That's what I mean. Yeah. And of course, this is important information for you because this means that I also can use a linear model in order to explain nonlinear relationships, because this is obviously a linear relationship in terms of logarithmic variables. We call this a log linear relationship, but it's not linear anymore. So that means we are able to explain nonlinear relationships. For instance, I also could regress. Sometimes we do something like this. That means I square the axis multiplied by beta plus epsilon I. So this is now a quadratic relationship I can capture. Yeah, and I can, on top, I also can put in the axis without a square, and then I need another variable name. Let's call it gamma now, the parameters, plus epsilon. So this is now a model which combines a linear term and a quadratic term. This gives you already quite some flexibility to capture a nonlinear relationship between y and x. Yeah? These kind of parameterizations are used quite often. But this is all a linear model, still a linear model. Okay, I think we have to stop here. So see you next Tuesday. And I'm still available for 5 minutes for the people in Zoom to answer some questions. Okay, thank you. So, are there questions? No questions from Zoom? Okay, doesn't seem to be the case. You have a question? So 1 second, I just stopped the recording.
Recording stopped.
I have a question.
1 second, I have a question, a live question here. Sorry. Okay. Yes.
I cannot load the packages, and this one especially, the ECDAT. I tried reinstalling R, and when I tried to install the packages with the thing I should install, but it just simply doesn't work.
Go on install.
Yeah.
Put in the name of the package and look for it.
That
Yeah.
times and it just doesn't work. That's why I thought maybe. So now when I try to run the ECDAT,
Then you have to load it in. You have to click on it again. You have to, you have to load it and you have to activate it.
okay.
No, you just click on it. You just hold the cursor on this line and then just click on command and enter. Yeah. Okay. Yeah. Something went wrong here. Okay. Yes.
I think that the final exam was set on January 27th.
Yeah.
And probably at the lecture time, right?
Yes.
Yes, and there's an overlap with one of the basic lecture, basic finance. So
I mean,
what can we do?
It's my lecture.
Yeah.
It's the lecture time.
So the people
cannot do anything.
If someone wants to do the final exam, they should not take the basic finance lecture exam. Because
well, I don't understand why this is at the same.
Yeah,
but that's
me
not.
neither,
But
because
they should move. I use my normal lecture slot. That's it.
Yes, they are not using the normal slot, so
And they should move. Yeah.
Okay, thank you.
Question about project. You know, somehow impediment and the read probably I will have which is the calculations of the universe. So like I want to do small projects or examinations. So I want to ask if, I don't know which day, but that week will be maybe it at the end of the week or in the
Okay,
beginning. So
okay.
I want
Yeah,
to
but
ask
let's.
if I can do this project alone or I have to do this group. If you say this group, okay, I will do it.
No, it will be group work anyway.
I'm just
But just let's talk about this maybe in a few weeks. And we will find some solution.
Thank you so much.
Okay, now in Zoom, you have to speak up a bit. I have to. Okay.
Yeah, so the recording is not going to be uploaded, no?
Speak up, please. It's a little bit quiet. I have to see how I can. So I cannot hear you too well.
So the recordings,
Okay. Yeah.
recordings of the lectures are not going to be uploaded.
No, not at this point. You have to follow. I mean, the reasons are obvious. Okay, other questions? I cannot hear you.
I have a question about the writing exam. Can you hear me, sir, please?
There is some, do you have some, you have several microphones on? What's the problem here?
Must be on your side. I mean, please mute.
Can you hear me now, please? Hello?
Okay.
Yes, sir. Can you hear me, sir, please? But I was asking, my question is about the writing exam. I was asking during the writing exam,
I cannot.
will we,
There's a technical problem. I don't know. Interference with different microphones. I guess.
sorry. No. Quand on regarde le site, pardon,
De quoi?
une la connexion.
Okay, try it again. So please ask.
Attends, je vais parler comme ça. Hello, sir.
Yeah.
Yeah, I was saying, sir, during the writing exam, should we fill ourselves or should we only interpret the data?
Which exam? The final exam. Final
Yeah, the
exam
writing
will be
one.
everything.
Yes.
The final exam, I mean, you will get multiple choice questions, analytical questions, you have to interpret data. I mean, it will be a
Yes, sir.
mix of everything.
Okay, sir. Thank you. Thank you, sir.
Okay, other questions?
No, sir, thank you.
Other people, maybe people, so I will not answer the chat. So if you have urgent questions in the chat, then please do it here.
Thank you, sir.
Hello.
Yes.
Hi, thank you so much for giving us the opportunity to ask questions. I just want to know, because you mentioned there are probably some students who are not as far as other in terms of econometrics. I was just wondering, if I go after class through the slides again and I see I have some issues, I want to ask if it's possible to come to your office hours instead of discussing it in class, so I don't take up too much time in class.
Of course, of course.
Okay, so I just have to write an email and ask for an appointment, or just
Yeah, in the
okay.
moment I do it that way. I mean, if too many people will write emails, then I probably will pool and make an office hour, a regular office hour. In the moment I do it on an individual basis. You can come to me. You also can arrange an appointment with the tutor.
Thank you.
Okay, yes. There's a hand raised, so please go on, ask questions. No more questions? Okay, last possibility to ask questions, because then I will shut off. See you, hopefully in class. Bye-bye. Bye.